This first session today is a theory session. I want to discuss the modeling of dynamic oligopoly. I gave you a preview of some of the issues last week in the opening talk. Suppose that we're interested in studying a industry of oligopolists. That means that there are just a few firms, and actually for today's purposes, I'm going to assume that there are exactly two, but actually everything I say will hold for more than two as long as the firms are big enough so that they have to take into account the other players' behavior. And in particular, I want to focus on the case where these firms are interacting not just once, but many times. So it's a dynamic setting, not a static setting. Well, then we run into an almost immediate modeling problem, which is that if we do the normal thing, which is to look at the Nash equilibria or the subgame perfect equilibria of the dynamic game, there are a huge number of them. And there's a result which I imagine you all know called the Folk theorem, which says that, well, it's not literally true that anything can happen, but that's a pretty good approximation. So there are lots and lots of equilibria, and all sorts of behaviors are consistent with equilibrium. So what do we do about that? One popular approach, and this is the approach I want to emphasize today, is to look not at all the equilibria, but at a particularly interesting subset called the Markov perfect equilibria. I'll give you a more precise definition pretty soon, but informally, the idea is that strategies don't depend on everything that happens in the past, but rather those aspects of the past which still enter the player's payoff functions, either now or in the future. And that means that we're looking at equilibria where the strategies are as simple as possible while still being consistent with profit maximization. These strategies are not depending on anything which is not directly entering the payoff function. So let's look at an example, and I think the example will make things pretty clear. Imagine that players are playing a game in periods 1, 2, 3, and so on. It's a dynamic game. And in each period, player I chooses an action. And the n-tuple of actions I'll denote by AT. So that's the n-tuple of actions in period T. And let's imagine that in period T, player I's payoff depends on the actions in that period, AT, and some state of the system, theta T, which might, since we're talking about oligopoly, correspond to current demand conditions. We'll suppose that the state of the system, theta T, might depend on actions that were taken before, and the state of the system that that existed before. But actually, it could depend on more than this. This is one of the simpler versions of the equation determining the state of the system. I think I saw a question. Yeah.
Is a pair function varying over time because there's a small t as a g, small suffix t?
I'm sorry, I didn't catch
the payoff function varying over time also?
The payoff. Yes, we're allowing the payoff function to vary over time. That's what the subset T means. Yes. Yeah. There's no at this level of generality. There's no need to make the payoff in period T the same every period.
So this theta t depends on f of a t minus 1. So it's just the last period. So is it because of that the name Markov is coming?
No. It could depend on more actions. You'll see where the Markov part comes in a minute. So the overall payoff for player I is just the discounted sum of payoffs, where delta is the discount factor. So this is the thing that player I is interested in maximizing. Any questions about that? Well, let's look at player I's maximization problem in period T. The history of the game up to that point is just everything that's happened up to that point. So the actions that have been taken and the states that have occurred, including the state in period T, because we'll suppose that player I sees the state in period T before acting in period T. So in principle, player I's strategy could depend on this entire vector of past outcomes. But you'll notice that the only components of this vector that actually enter player I's payoff function in period T is theta T. All of the other variables are no longer relevant. And all player I is interested in period T is his payoff that period and in future periods. Actually, these components don't enter his future payoffs at all. So the only payoff relevant variable in period T is theta T. And that means that a Markov strategy should depend just on theta T and nothing else. And now we can define what we mean by a Markov perfect equilibrium. It's simply a subgame perfect equilibrium. So players are maximizing not just at the beginning of the game, but in every subsequent subgame. And they're using Markov strategies. Now, because the equilibria are subgame perfect, players do not suffer from restricting attention to Markov strategies. That is, they are fully maximizing. But it turns out that because the other players are using Markov strategies, it doesn't hurt me to use Markov strategies too. And in fact, you can show that a Markov perfect equilibrium exists basically under the same conditions that an ordinary subgame perfect equilibrium exists, even though it's a more restrictive concept. Now, one thing that Markov equilibrium typically does is to dramatically reduce the equilibrium set. And one simple way of seeing that is to look at a famous dynamic game, maybe the most famous of all, the repeated prisoner's dilemma. So this is the prisoner's dilemma. Imagine that this is played over and over again and players maximize their discounted sum of payoffs. Well, of course, there are a huge number of subgame perfect equilibria. According to the Folk theorem, any convex combination of these payoffs with such that players are getting at least 0. 0 is the minimax point, can be sustained as the average payoffs of a subgame perfect equilibrium as long as there's not too much discounting. So that's a lot of payoffs. But for the repeated prisoner's dilemma, the state of the system is actually null. That is, nothing about past history matters when you're playing the game today. So players don't have to look back at all. But if they're not looking back at all, that means that Markov strategies can't depend on the past at all. And that means that the only possible Markov perfect equilibrium is the same play that you would get in a one-shot game. Players will play D for defect rather than C for cooperate. So we just get an infinite repetition of DD. Now that's a very extreme case where we reduce a huge equilibrium set to a single point. And that extreme outcome is due to the fact that there's no aspect of history which matters. I'm going to be interested this morning in cases where the past does matter, at least somewhat. And in those cases, we're not typically going to have a unique equilibrium, but we will certainly reduce the equilibrium set a lot, and in ways that make the analysis of the equilibrium set much more manageable than when we're confronted by the Folk theorem. So Markov perfect equilibrium typically does have real cutting power. Now just a word or two on the theoretical foundations of Markov perfect equilibrium. As I said, conceptually it's getting at the idea that players are behaving in as simple a way as is consistent with rationality. Another way of thinking of it is that if you're in a game with someone else, and something has happened that doesn't actually affect either of you anymore, well, you should let it go. The old expression is bygones are bygones. It shouldn't affect your behavior anymore. Or put another way, if the only reason that I'm conditioning on some aspect of the past is that you're doing it, and the only reason that you're doing it is that I'm doing it. That's called bootstrapping. For Markov equilibrium purposes, we try to rule out bootstrapping, where a dependence on the past is created only because the other guy is doing it, and he's only doing it because you're doing it. There are some. There's a substantial literature on theoretical foundations, and if you want references to that, I'd be happy to give them to you. But that's all I propose to say this morning about the philosophy behind Markov equilibrium. I imagine you've probably seen it in one form or another before. So let's take this concept and now apply it to some dynamic oligopoly models. Question?
Generally, the minimal discount condition still applies? Or in this kind of equilibrium, well, we typically need a minimal discount factor?
Well, put it this way. You will get existence of Markov perfect equilibria for any discount factor, but the equilibria will tend to be particularly simple when the discount factor is close to 1. So yes, many of the results will be for discount factors which are close to 1, but that's not because that's not because you need delta to be close to 1 to get an equilibrium. It's to make sure that the equilibrium is simple. In particular, players don't care that much about what happens in a particular period. They're looking to the longer term. So let me begin by looking at a model, a duopoly, where there's a large fixed cost of production. I say fixed cost rather than sunk cost. So if you're not producing, you don't incur the fixed cost. If you are producing, you have to incur it. Oh, and by the way, well, there are references on the final slide of this presentation, but a lot of what I'm going to be saying from now on is in 2 papers that I wrote with Tirol in about 30 years ago now. In Econometrica. It's called A Theory of Dynamic Oligopoly, Parts 1 and 2. They're published back to back in the same issue. So there's a large fixed cost of production. That means that only one firm is going to be able to operate profitably, but there are 2 firms that could operate. Well, there's an old idea in I/O which was developed at length by Baumol, Panzer, and Willig, which says, it's called contestability, and it says that under these circumstances where only one firm can operate, but there are multiple firms that could operate, we should get a pretty competitive outcome, despite the fact that it looks as though we have a monopolist. In other words, potential competition should be just about as effective as actual competition, because if the incumbent firm is getting a lot of profits, well, the other firm might then try to come in and force the incumbent out. That's the idea, but the question is how to model this. It's pretty hard to model statically. If we look at a model where firms are choosing their quantities in Cournot fashion simultaneously, that is a static model, and there's a large fixed cost, then there are going to be three equilibrium outcomes. There's one where firm 1 produces at the monopoly level and firm 2 stays out. There's the mirror image of that where 2 is the monopolist, 1 stays out, and then there's going to be a mixed strategy equilibrium where the two firms randomize between staying out and producing. In that case, they won't produce at the monopoly level. It'll be somewhat lower. But none of these three gets at the contestability idea. Maybe the third one slightly gets at it, but not very well. So we're going to need a truly dynamic model to capture this contestability notion. So let's do that. So firms are going to be choosing outputs in each period. Now, here is the twist. Rather than each firm choosing an output every period, which would make the game essentially a repeated game, we're going to suppose that firms choose outputs in alternating periods. So firm 1 chooses outputs in periods 1, 3, 5, etc. Firm 2 in 2, 4, 6, etc. And the point is, well, actually there are 2 points. The idea that we're just looking at quantities goes back to the Krebs-Schenkman paper that I was talking about last week, which says that we can think of quantity competition as really a reduced form for a fully fledged model in which firms are choosing capacities in the medium term and prices in the short term. So we're going to make that reduction in this model. Firms are choosing quantities, but you should think of that as capacities plus prices. But the point is that a firm that acts in period 2 is committed to its quantity, or think of that as its capacity, until it moves again 2 periods later. So we're getting at the idea that firms cannot change capacities immediately. They're in effect committed, at least in the medium term, for 2 periods, to their capacity choices. And this is going to turn out to matter in a significant way. Yep.
Would you like to allow the capacity to be a constraint or an upper limit? I mean, if I have a facility that can make 100 units, I can always produce only 90. If I want to, but I cannot produce more than that in the next period. Right?
Right. So you've got this is the Krebs-Schenkman idea that the capacity gives you an upper limit, but then then price competition.
You choose the capacity, not the quantity.
You choose capacity, and then you choose a price, which then determines the quantity. That's right. So, but we're not going to look at prices, and we'll look at prices later today. But at the moment, we're just looking at the reduced form where firms are just choosing quantities. But you should think of that as capacity plus price. Yeah.
Sir, if each firm chooses quantity in each period, then just for a clarification, are we back in
Then we're
repeated
back.
game?
Then we're back in the repeated game, because then past quantities don't matter. So the reason for doing it this way is so that the quantity that you've chosen today really does matter for a while, and in particular, it's going to matter to the other firm when the other firm chooses its capacity. Now, of course, the idea that firms are literally alternating is artificial, but you can actually derive that from a more fundamental model where perhaps the time at which firms move is determined randomly, but once a firm moves, it's committed for a short period of time.
And just in that case, choosing the Cournot quantity is the only equilibrium, right?
In the case where there's no commitments, yes, then Cournot quantities are the only equilibrium. But we'll see that it's not true here. So here, this is just an example, but it's an example that I'm going to focus on. In period T, firm 1's profit is going to depend on the two quantities. Now, if firm 1 is moving in period T, then this quantity for firm 2 is actually the quantity that was chosen by 2 the previous period, but it still persists in period T. This is just Cournot revenue minus the fixed cost, which has been chosen at 1/8 because it turns out that at 1/8 one firm but not 2 can make positive profit. And as we've been saying, firms are interested in their overall discounted profit. So what is a Markov strategy in this model? Well, it's a strategy in which in period T, odd period T, so firm 1 is moving, firm 1 makes its quantity choice this period depend only on the quantity choice that the other firm took the previous period.
One question.
Yes.
Should we think about that as having some sort of fixed factor that is getting depleted as you produce, or like how should we think about QT1 times the rest?
So
In the production,
so this is the price. Yeah, it's a linear demand. This is just Cournot duopoly with a linear demand function. So this is the price. This is the quantity. There are no variable costs, only a fixed cost. Okay. So let's characterize the symmetric Markov equilibria, Markov perfect equilibria of this model. There's actually a unique equilibrium. So this is very different from the folk theorem of repeated games, where there are lots of symmetric equilibria. Here there's one. So here's one of the cases where having delta close to 1 helps. If delta is not close to 1, there will still be a unique Markov perfect equilibrium, but it may be a little bit more complicated than this, which is very simple. What this says is that there's going to be a deterrence level, we'll call it a deterrence level, Q bar, where if you are, if the other firm is producing less than the deterrence level, then you will react by coming in and producing Q bar. But if the other firm is producing at or above the deterrence level, then you stay out. And Q bar solves this equation. This says that if the other firm is producing Q bar, and you come in and you produce Q bar too, well, you're going to knock the other firm out according to these strategies here. But overall, you're going to earn 0 profit. So Q bar is the break-even point. If the other firm is producing a Q bar, you come in, you're going to knock him out and overall make a 0 profit. And notice that if delta is close to 1, then this term blows up, gets big. This is going to be positive because if the other firm is out, you're going to earn a positive profit. But the only way that this equation can hold is if this is positive but small. So that means you will earn a positive profit, but not much of one. It's going to be a pretty competitive industry. So that's the main result for this model, and I want to take a few minutes to go through the argument for why this is true, but let me just pause to make sure everyone's with me. Any questions about the statement of this proposition? Is it clear? Yeah.
Something else. So, sir, from a technical point, so the firm which moves in the first period, so then what quantity does that firm assumes of the other firm?
Okay, so all right. Strictly speaking, the first firm to move is going to choose Q bar.
Absolutely.
Q bar. Now, the way to think of this, though, I mean, formally speaking, there is a first period, but we shouldn't think conceptually of there being a first period. We should think of this as being determined just more or less by accident. Whoever gets there first is going to take over the market. That's the idea. That's the idea that we're trying to capture. Now, formally, there has to be a first period, but that's only a modeling quirk.
Somewhat it also captures the idea of first mover advantage.
Yes, actually, I think I have this on the slide. Yes, this is Stackelberg leadership, which I talked about last week. So this is the dynamic, contestable version of Stackelberg leadership. If you get there first, you get the market. You're not going to get that much out of it. Your profit is going to be pretty low, but nevertheless, you will have a positive profit. The firm that's out will not get anything at all. I think I saw another question. Everyone happy with the proposition? Well, whether you're happy or not, I'm afraid that it's a fact of life. But a proposition is a proposition, but let me show you quickly why it's true. The first step is to show that the Markov strategies are, actually it should be non-increasing. Sorry about, I'll correct that. If the other firm increases its quantity, you're going to decrease yours. Now, how do we show this? Well, let's imagine that firm 1 chooses Q this period. And let W1 of Q be one's continuation payoff starting the next period. So remember, firm 1 is committed to that Q next period. Let W1 of Q be one's continuation equilibrium starting in that next period. Then this expression here is firm 1's total payoff, right? This is his payoff this period, and this is his payoff starting in the next period. So for equilibrium, it has to be the case that his overall profits, discounted sum of profits, is great from using the optimal reaction to Q as it would be using some other quantity, or think of it as an optimal reaction to Q prime. No, for any Q prime. This just says that SQ is optimal against Q. We can do the same thing, assuming that the other firm has chosen Q prime. We have a corresponding inequality for Q prime. And now we can basically subtract the second inequality from the first by multiplying it by -1 and then adding. And that's going to eliminate the W's. And we'll be left with an expression like this. Now, the cross-partial derivative of the profit function is negative. If we go back to this expression here, if you differentiate first with respect to Q1 and then with respect to Q2, you get -1. So that's negative, and that means that from this inequality, that if Q is bigger than Q prime, then S of Q has to be less than or equal to S of Q prime. I belabored this argument. I've spelled out this argument because this is a typical kind of argument that goes on in the dynamic oligopoly literature for trying to characterize the Markov equilibrium strategies. So now we know that the equilibrium strategies are non-increasing. Next claim. Suppose that firm 1 reacts to firm 2 by choosing a positive quantity. So suppose S of Q is positive, then it better be the case that S of Q is actually bigger than Q. Let's see why that's so. suppose S of Q were less than Q. Well, we've shown, the first claim shows that S of Q is actually decreasing in Q. So that means that the other firm is going to react to S of Q by choosing something bigger than this. So this is what, if this is firm 1, this is how firm 2 will react. And 1 will react to that by choosing something less than what 2 does. We're going to go back and forth with 2 always outproducing 1. This just follows from the logic of S of Q being decreasing. 2 will always outproduce 1, which means that 1 can't possibly make a positive profit. 1's profit is going to have to be negative, because it's always producing less than firm 2. But that means if it's going to be making a negative profit, it's better off not producing at all. And so we can't have S of Q less than Q if it's positive. It has to be greater than Q. If this isn't immediately clear, just think about it quietly for a minute or two, and I'm sure you'll see it. The next claim is that there's going to be a deterrence level, Q bar, such that if you're producing above, this should be actually greater than or equal to Q bar. If you're producing at or above Q bar, that keeps the other firm out. And if you're producing less than Q bar, the other firm is going to produce a positive amount. And we know from the previous claim that if the other firm produces a positive amount, it's actually going to be more than Q. Now, why is this true? Well, we know, you can see that if the other firm is producing nothing, then you should certainly come in. So Q bar is not going to be 0. Let's look at a sequence of bigger and bigger Qs, Qn going to infinity. At some point, you're going to be deterred. That is, eventually, Qn will be so big that you're not going to want to come in. You can't possibly make a positive overall profit if you do. So for any bigger Q than the one where this first occurs, you're going to be deterred. Let's look at the smallest possible Qn for which this equation holds. That's going to be the deterrence level. And by definition, for any smaller Q, you're not going to be deterred. So the next claim is that if you manage to deter the other firm this period, then the other firm in equilibrium is going to stay out forever. That is, it's not going to come back at any later date. Why is that? Well, if you're producing more than Q bar, then since Q bar is the deterrence level, it's certainly going to be the case that the other firm stays out next period. But if the other firm is out next period, you're going to want to be in next period, the next time you can move. But now we're going to be in another one of these back and forth situations. So here's Q, here's Q bar. S of Q is 0. S of Q is positive because the Markov strategies are non-increasing. And so this firm is always going to be outproducing this firm. And we already saw that if you're always outproduced, then you should produce 0, because otherwise you will have a negative profit. So that means that once you've knocked the other firm out of the market, it stays out for good. Now, the next claim is really the only point in this argument where we're using the fact that delta is close to 1. If delta is close to 1, then the deterrence level actually has to be bigger than the monopoly level. Well, suppose it were less. Well, that means that the monopoly level would deter a firm from entering. But then, if I'm producing at the monopoly level, this period, you can come in, produce at the monopoly level this period, and that's going to knock me out because we're supposing for the moment that the monopoly level is bigger than the deterrence level. This should be Q bar. Sorry about the typo. So there's a bar over Q. So overall profit is certainly going to be positive. And actually, if delta is close to 1, it's going to be pretty big because this is positive, and as delta gets close to 1, it's going to blow up, get bigger and bigger. So that tells us that QM will not actually deter. The other firm has the incentive to come in at the monopoly level because it'll make a positive profit overall. So we cannot have this inequality. The deterrence level has to be bigger than the monopoly level. Right.
In claim 4, does a firm have an incentive to produce more than Q bar?
Well, it might. If delta is not close to 1, then Q bar could be less than the monopoly level, and in that case, a firm might produce more than Q bar. So here is how delta being close to 1 simplifies the analysis. Suppose that delta were not close to 1, and the other firm is currently in, but not at the deterrence level. The other firm is producing, but below the deterrence level. Then what you might want to do is to come in at the deterrence level, which could be less than the monopoly level, That'll knock the other firm out. Once the other firm is out, then you want to increase your output to the monopoly level. So you see, if delta's far away from 1, behavior is a little bit more complicated. There might be a two-step adjustment where you first knock the other firm out. You don't want to produce at the monopoly level then because you might get negative profit because the other firm is producing too. So you'll produce at a lower level, knock the other firm out, and only then you'll move to the monopoly level. If delta is close to 1, you can do this in one step. You go directly to the deterrence level, and you stay there. And you don't want to produce more than the deterrence level because you're already above monopoly output. You want to produce the least possible quantity which will deter the other firm. Okay. And then the final step is just to confirm the assertion we made in the proposition, which is that this is the behavior, the equilibrium behavior. If the other firm is producing less than the deterrence level, you produce the deterrence level. If the other firm is producing more than the deterrence level, you stay out. So really, the only thing we have to show, we've already shown that if you produce more than the deterrence level, the other firm stays out. The only thing we have to show is that if you are producing less than the deterrence level, the other firm is going to react by producing Q bar. Now, we can't have the other firm reacting to Q less than Q bar by producing a positive quantity that's less than Q, right? This was one of the previous claims. If you react to the other firm by producing a positive quantity, you better be outproducing the other firm. Otherwise, you're going to make negative profit. So if this inequality holds, then you're going to stay out. But that contradicts the fact that Q bar is the deterrence level. You can't react to Q less than Q bar by producing nothing, because otherwise Q would deter you, and Q is less than the deterrence level. So it has to be the case that if you're producing at a positive level when the other firm is producing Q, that you're outproducing the other firm. But then that means that the other firm is going to react to you by staying out. That was, again, a previous claim. But if the other firm is reacting to you by staying out, then you must be producing at or above the deterrence level, by definition. You're not going to produce above the deterrence level because that's unnecessary. Q bar will deter. Any extra outputs reduces your profit because you're already above the monopoly level, so you will produce right at Q bar. And that's it. That I went through that pretty quickly to give you a flavor of the kind of argument we see in this literature. If you want to check the details, well, I'll post the slides, but you can also read even more details in the original article.
Generally, is Q bar increasing in delta?
Q bar is increasing in delta, yes. As delta goes to 1, you have to produce more and more to deter, and eventually eventually you're going to be getting essentially zero profit. That's the contestability result. That even though you're in the market, you're getting basically zero profit every period.
Is it possible to test this if you have a set of oligopoly markets and you have a negative shock in fixed cost?
Mm-hmm.
That this implies that you should observe a decrease in the quantity produced by both firms.
If you have a negative shock to profits,
No, to fixed cost. Yeah,
or a negative shock to fixed cost, you mean fixed cost goes up?
yeah, or goes down. You
Yeah.
should observe a variation in the quantities because of
yeah,
a change in the demand level.
Exactly. So this has many empirical consequences, and one is that Q bar should depend on the size of the fixed cost. Absolutely.
The super games literature generated an enormous kind of anything goes result, but
Yes.
this is also generating an extremely stark prediction in the other direction. So
Yes.
I mean, it is an improvement over anything goes, but
Yes.
it's sort of, actual markets are going to end up somewhere in between, I guess.
That's
don't
right.
see one
That's right.
firm.
So the contestability literature itself is looking at one corner of the spectrum of possibilities where you have monopoly or near monopoly, but at zero profits. This model is not geared to explain all oligopoly outputs. It's geared to capturing the contestability idea. But I hope that although we focused on contestability, this gives you the idea that even in markets where we might have two or more firms operating, we're not going to have a huge number of equilibria. We may not have a unique equilibrium, but we're not going to have a lot of equilibria. So we'll have a manageable number. Now, in a moment, I'm going to turn to another class of models, price models, and you'll see there that there are multiple equilibria, but the set of equilibria is still manageable, and we can characterize them. There'll be two classes of them, and they'll each have a nice characterization. Any other questions about the large fixed cost model before we move on? Okay, so now I want to turn to competition explicitly in prices, and this is the other paper in that old issue of Econometrica. And in almost every respect, the model is going to look like the quantity model, except that now we'll suppose that capacity is not an issue. So the sort of market we should have in mind is maybe two gas stations, gasoline stations, near one another. They're the only gas stations around, so it's a duopoly, but they can get as much gas as they need at fixed cost. So capacity is essentially infinite. Once again, we're going to adopt this alternating moves perspective, and we're going to assume that firms are committed in the short run to prices. So if I choose a price in period t, it persists until period t plus 2. Now, this is just a modeling device. If prices were continuous, then, and here we're essentially going to be in a Bertrand model where the firm that chooses the lower price gets the whole market. Then if you wanted to undercut the other firm, you would want to cut your price by epsilon. And then you get the whole market. Well, cutting by epsilon, where epsilon is arbitrarily small, is not so easy to handle in a formal model. So rather than allowing for any price, we'll suppose that there's a finite set of prices which approximates the continuum but is finite. But we'll suppose that this finite set is rich enough so that maybe prices differ from one another by some small quantity, maybe a penny. And because this is a Bertrand model, we'll look at both firms are producing the same good. So we can look at market demand at a particular price. And this is pi of p is just total market profits at price p. This is just the Bertrand setup for individual firms. You get the entire market profits if you're charging the lower price. If the other firm is choosing the lower price, you get nothing. Everyone goes to the other firm. And if you're charging the same price, you split the market profit. So that's the model. And I want to characterize the Markov equilibria of this model. And it turns out that that's quite easy to do. Once again, the only payoff relevant variable is the price the other firm chose last period. There are two kinds of Markov perfect equilibria in this model. One can be thought of as Kinked demand curve equilibria. I talked about the Kinked demand curve, which goes back to Hall and Hitch and Sweezy in the opening lecture. This is going to be a dynamic formalization of that idea. The other kind of equilibrium is what we might call an Edgeworth cycle equilibrium. That goes back to Edgeworth, who was commenting on Bertrand. So what do these equilibria look like? Let's start with the Kinked demand curve equilibrium. Here's an example. Suppose that there were 7 different prices you could choose. So there's 0, P1, P2, up to P6. And for each price, this is going to be the Markov strategy reaction to that price. So if the other firm was choosing P6, you react by playing P4, and so on. Well, what's going to happen? We're going to have a steady state at P4. If the other firm charges P4, you charge P4, and we stay there. And the reason we stay there is that if any firm cut its price, say to P3, that would initiate a price war. The reaction to P3 would be P2, the reaction to P2 would be P1. Once we're at P1, we go back to P4. But in the course of this price war, firms will be losing the profit they could have had if they had just stayed at P4 in the first place. So they won't cut their price. They will stay at P4. And you can think of this as a model of tacit collusion. They're going to get a reasonably high profit out of this, P4 profits, which is enforced by the threat of a price war. And furthermore, the price war does not involve strategies that depend on anything that's payoff irrelevant. So the fact that we're looking at Markov strategies pins down to a great extent the nature of the price war needed to enforce the high price of P4. If you tried to raise your price above P4, say to P5 or P6, the other firm wouldn't follow. So you would be losing your entire market in that case. So you're not going to do that.
Is it that is it have to be a symmetric case only, or could we have a possibility that it's the partition is so fine that P4, P5 are somewhat...
So there do exist asymmetric, there do exist asymmetric equilibria. I'm not going to talk about them, that you can read about them in the paper. But they still have this same general feature that the two firms are at the steady state, and then that's enforced by the threat of a price war. But the two firms will be behaving a little bit differently from each other in the price war.
But a symmetric equilibrium must exist, right?
Yes.
Because the game is symmetric.
Because the game is symmetric. So you always get a symmetric Markov perfect equilibrium. Yeah.
I'm just not sure what happened. You're assuming a Kinked demand curve?
Yes. This is just an example of a Kinked demand curve equilibrium. And now I'm going to make an assertion, which is proven in the paper, that they always exist, and
regardless of the actual form of the demand.
Right. Yeah.
It's still there on the board also. No.
Yes, there's the Kinked demand. Yes. Kinked demand curves have longevity. But a Kinked demand curve is really a tacit collusion equilibrium. It wasn't expressed that way by Hall and Hitch, but that's in a dynamic setting. That's what it really is. So here is the assertion, the more general assertion that they'll always exist in equilibrium with a steady state price, P star, and if in such an equilibrium, if a firm chooses a lower price, but still above this, this minimum price, P lower bar, then the other firm reacts by lowering its price even more. So that's the price war feature. And the price war continues until it reaches this very low price, P lower bar, and at that point the firms go back to the steady state. Yeah.
So just a clarification, the term Kinked demand curve isn't it misleading in the sense that they are technically the reaction curves, right? That it's a price, you give me a price of other firm and I will, but the demand curve is like price and...
Yeah, okay. So the term goes back to Hall and Hitch, and you're right, it's it's actually a dynamic reaction curve. They did not have a dynamic model, so they described it as a static kink demand curve equilibrium, but I think this is the right way of doing it.
So means that given this equilibrium reaction curves,
Mm-hmm.
if I draw the equivalent demand curve, it will be a kink type.
Yes, that's right. That's right. If you lower your price a little bit, that's going to it's not going to increase demand a lot because the other firm is going to equal that or match it. Lower price even more. If you raise your price, demand is going to fall off because the other firm doesn't follow. So that's this. So there's going to be a class of kink demand curve equilibria of this form. And in fact, P star is not going to be uniquely pinned down. It can't be too high. If it were very high, then it would pay the other firm to lower its price, even if that initiated a price war, because at least temporarily it would be getting higher profits. And a P star can't be too low because otherwise it would pay one of the firms to raise its price. The other firm would want to follow because the other firm would be getting more profit even if temporarily. And in fact, we can characterize the exact interval that P star must lie in. It turns out that if P star is above the monopoly price, firms must be earning at least 2/3 of the monopoly profits. And if P star is below the monopoly price, firms must be earning at least 4/7 of the monopoly profit. Now, where do these fractions come from? Let me quickly show you how the argument goes there. Let's look at P star above the monopoly point. So we want it to be the case that in equilibrium firms are willing to stay at P star. It's the steady state. And if they do stay at P star, they're each going to get overall profits equal to this. Now what happens if a firm undercuts to the monopoly price? In the period where it's undercutting, it's going to get monopoly profits. Now, we don't know exactly what happens after that. It depends how the other firm reacts. So, but at worst, this firm is going to be getting 0 the next period. In the period after that, the firm always has the option of going back to P star, and it knows how the other firm will react to P star because P star is, by assumption, a steady state price. So once it goes back to P star and the other firm has reacted to that, the firm is going to be getting this profit again. So it cannot, for equilibrium, it cannot be the case that this profit is bigger than this profit. Otherwise, firms wouldn't be willing to stay at P star. And if you write out that inequality, and simplify it, you get this, which implies that profit at P star must be at least 2/3 of the monopoly profit. And there's a corresponding argument if P star is less than the monopoly, is less than the monopoly price. I'll leave it to you to investigate that. What I want to turn to now, though, is the other kind of equilibrium. In Kinked demand curve equilibria, we get a steady state. Out of the steady state, which could happen because of some shock to the system, we'll have price wars. But in the steady state, we get P star all the time. In an Edgeworth cycle, the price is always changing. So here is an example where maybe we start at P4, we work our way down to P1, but then we go back to P4 again and work our way down. We saw such an example yesterday. John Asker was talking about Edgeworth cycles in Australia. They've been observed many other places too. This is going to be an equilibrium model behind Edgeworth cycles. And of course, this is just an example, but more generally, you can show that there will always exist an Edgeworth cycle in which there's a maximum price P upper bar, a minimum price P lower bar, and basically starting at the maximum price, we move down till we get to the minimum price and then go back to the maximum again. If a firm goes above the maximum price, the other firm doesn't follow. If the firm goes below the minimum price, the other firm goes back to the maximum. We can characterize, just as we characterized where P star must be in Kinked demand curve equilibrium, we can use the same kind of inequalities to put bounds on P upper bar and P lower bar. Yeah.
Should we be troubled by delta near 1? Like, is this reasonable, or how
Okay.
how should I think about it?
Well, okay, so one way of thinking of delta near 1 is the idea that although you are committed to prices for a period of time, that you're not committed to them for very long. So the next price, the next time you're going to get to choose a price will be pretty soon from now, meaning that the interval over which you're discounting is small. I think that's the way to think of it.
So you're actually not really, it's not, there's no real lag. The lag is a modeling technique.
Yeah, it is a modeling technique, absolutely, but it has real economic meaning, which is that the other firm is reacting to the price that you're choosing now, rather than to any irrelevant variables that you might have chosen in the past. So there is real economic content to it, although it's a modeling device too. Yes, yes, that's right. Strictly speaking, if you raise your price, you're going to lose all your demand. That in the instantiation that I was presenting. That's right. So it's. But that's only because we were looking at extreme Bertrand competition where firms are producing exactly the same kind of goods. If there was some product differentiation, then we would get a true kink. Yep.
How the results are robust? I mean, the robustness of the results
Yeah.
to imperfect.
Oh, so the question is the propositions that I presented, in particular characterizing the range of P stars, are those robust to introducing imperfect substitutes between the two firms' goods? The answer is we didn't look at that. I mean, I see no reason why there shouldn't be equivalent, corresponding results if you get some imperfect substitutability, but we didn't actually analyze that. That's an open question, which some of you might want to look
much of this is it's an example, right? So you
Yeah.
saw yesterday in the retail market where they aren't perfect substitutes, they're across the street, they don't know different brands of things. You still get it. Okay.
Yeah.
So the whole issue of the theory is to provide, let you see what kind of model you should be building to rationalize that.
That's right. That's right. So here is the general statement about what can go on in this model. I've shown you Kinked demand curve equilibria. I've shown you Edgeworth cycle equilibria. In fact, that's all you get. You get a class of Kinked demand curve equilibria. You get a class of Edgeworth cycle equilibria. In both cases, we can say something about what the bounds on those equilibria are, and you don't get any other equilibria in addition.
That doesn't generalize.
Right. Well, it generalizes in the sense that if we started introducing imperfect substitutes, we might get other equilibria, but they would look, if we weren't too far away from perfect substitutes, they wouldn't look too much different from these. We wouldn't suddenly get an equilibrium which is extremely different. One more point. Often, equilibria, collusive equilibria, are criticized by theorists especially for not holding up to renegotiation. So let's look at the classic way of enforcing collusion. It's not the way that we're enforcing collusion here, but the way that it's usually done, which is to have firms play monopoly prices or something near monopoly prices, and then if either firm deviates, they go to the one-shot Bertrand equilibrium. So trigger strategy equilibrium. There's a theoretical problem with that, which is that once the deviation occurs, firms don't really want to carry out the punishment. They don't want to go to one-shot Bertrand because they both lose. They have an incentive to say to one another, explicitly or implicitly, let bygones be bygones. Let's go back to the collusive equilibrium again. So the equilibrium is not renegotiation proof. And formally speaking, an equilibrium is not renegotiation proof if there's another equilibrium which both players prefer. Now, what about in the Markov perfect equilibrium models we've been looking at? Let's look at the price model. Well, it turns out there is a renegotiation proof equilibrium. It looks something like the trigger strategy equilibrium, but it's not the trigger strategy equilibrium. There is this floor, P lower bar, and if someone deviates by cutting a price, the other firm reacts by going down to the floor, but then afterwards they go back to playing the monopoly price again. So they don't stay at the floor forever. They go back to cooperating. And that's renegotiation proof because of the commitment. If the other firm has cut its price, if I went directly back to the monopoly price, if I said let bygones be bygones, I would lose profit because the other firm is committed to that lower price, at least for a while. So I don't want to go back to the monopoly price now. I'm better off going down to P lower bar. Now, once we're at P lower bar, then, and we're both making presumably very low profit, then we have an incentive to go back to the monopoly price, but not before profit has dropped so much that we're willing to make a temporary sacrifice to going back to a high price again. So this equilibrium will be renegotiation proof. And furthermore, it can be shown that among all of the Kinked demand curve and Edgeworth cycle equilibria that emerge in this model, this is the only one that's renegotiation proof. So if you believe that firms have the opportunity to renegotiate, then you get a Kinked demand curve equilibrium that looks like this. And that's all I have to say. Any final questions? Yeah.
There is something that I don't understand in the Markov equilibrium. If I don't take into account the past, how can I know what is the strategy of the other player? Since I know what is his strategy from seeing what he did in the past. But if you say that I don't care what he did in the past, is there no contradiction in the concept of Markov?
No.
Markov equilibrium?
So to know what the other firms, so the question is how can I know the other firm's strategy? Well, the other firm's strategy is S of Q. So the other firm, if you imagine that firms are learning these strategies rather than simply inferring them, so firms learn to use Markov strategies. Well, I see that in the past, whenever I played Q, you've played S of Q. So I see what you've done. You're not reacting to things that I've done before I chose Q. You're just reacting to Q. So that's how I learn your Markov strategy, by seeing that you behave, that you react to Q with S of Q.
But if you learn from what I did in the past, why you don't take it into account when you choose your strategy? Why you don't try to deter or to accumulate reputation? Why, for example, in the prisoner's dilemma, you will play always defect. Since if you see the past and I see the past, it means that we take the past into account. If we take the past into account, then let us take strategies that take the past into account and play conditional strategies.
Well, you're asking a question which is much broader than Markov equilibrium. You're asking, how can we ever get to equilibrium? Because unless I take your strategy as given, I always have an incentive to try to change your strategy by my behavior. That's a problem that exists for all of dynamic game theory. It's too big a question to resolve now, but it's certainly not a problem that is special to Markov equilibrium.
But in Markov, you take the past much less into account than
You take the other player's strategy as given. That is the same assumption that we make in all of game theory. You are reacting to a strategy by the other player that you are taking as fixed, and you're trying to optimize against that strategy. That's always true. It just happens that in this case, the strategy the other player is using is a Markov strategy.
So the lecture tonight is about that. Yeah.
Okay.
Exactly.
Good. You will get Ariel's expert view. But that's it for now. See you in a half hour.